Hi, my name is Lucas Weintraub, and today we're going to be proving trigonometric identities. So, the main categories that we're going to go over today are, number one, the Pythagorean identities, which are things that combine the Pythagorean theorem with trigonometry. We're also going to look at reciprocal identities, which are secant and cosecant, or 1 over cosine and 1 over sine, and quotient identities, which are cosine over sine and sine over cosine. There are also other identities like sum and difference, product, double angle formula, but today we're just going to focus on these three and how to combine them to prove other things. We're going to spend a lot of time looking at Pythagorean identities, and then we're going to look at examples. So, the first and most important identity in the Pythagorean identities is sine squared theta plus cosine squared theta is equal to 1. Another one is tangent squared theta plus 1 is equal to secant squared theta. And the last identity is 1 plus cotangent squared theta is equal to secant squared theta. So it's important to know these, but it's also important to know where they come from. It's really different when you know why you do the steps in a procedure versus just going through the motions and memorizing a procedure. So now I'm going to give a proof on each of these identities so that you can understand more how to do them. And if you already know why they exist, then you can skip to later in the video where I show some examples of verifying trig identities that use all of this stuff that I'm about to explain. So here's a proof of the first identity, which is sine squared theta plus cosine squared theta is equal to 1. So to start a proof, you don't really know where you're going to end up, but there is a motivation for what to do next. So since we want to end at this formula, we can start off with trying to find what sine and cosine mean in this triangle and maybe how to combine it with the Pythagorean theorem. So let's see what sine of theta is. So sine of theta is going to be opposite over hypotenuse, which is y over r. That means y is equal to r sine theta. Since y is the length of this side of the triangle and y is also r sine theta, that means we can replace it with r sine theta. So this side of the triangle is r sine theta. We can do a similar thing for this side because cosine theta is equal to x over r, adjacent over hypotenuse. That means x is equal to r cosine theta, and we can just plug it in. Now, we can use the Pythagorean theorem to combine all of these three sides. So this side squared, which is r squared cosine squared theta, plus this side squared, which is r squared sine squared theta, is equal to r squared. Now you can factor out an r squared from both sides, and then you would get this. And then you can divide by r squared on both sides, and what you're left with is the identity we were trying to prove. Great, so now we can use that to prove the other identities, 2 and 3, which were tangent squared theta plus 1 equals secant squared theta, and 1 plus cotangent squared theta is equal to cosecant squared theta. So the way that we're going to prove these is using what we just proved. So we start off with this identity. And to get to the first one, what we have to do is divide by cosine squared theta on both sides. So this turns into, you can split up the fraction like that. And I'm just going to simplify this thing right here. So 1 over cosine squared theta is, of course, the same as 1 over cosine times 1 over cosine. And 1 over cosine is equal to secant. So that's secant times secant, or secant squared. And that is our first reciprocal identity. And this right here is going to be our first quotient identity. Sine squared theta over cosine squared theta is equal to tangent squared theta. So that's quotient because it's the quotient of two things, namely sine and cosine. And since it's squared on both, it's going to be squared for tangent. Cosine squared over cosine squared is 1. And now we're left with the second identity. You can do the exact same argument to get the third one, 1 plus cotangent squared theta is equal to cosecant squared theta. But instead of dividing by cosine squared theta, you would divide by sine squared theta, and you would simplify. So now, here's how to prove other identities besides those three. So, the first thing to try. If there's a fraction, try using reciprocal and quotient identities. So if you ever see like something plus something all divided by something else, and it uses sine and cosine and secant, then you can try to apply some identities and to get to where you want to prove. The second thing to do is, if there's a square, try using Pythagorean identities. And by a square, I mean things like this, like cosine squared theta and sine squared theta. That's what I mean by squares. So something squared. Because if anything is squared, you could probably substitute it with something else from the Pythagorean identities. So now we're going to begin with some examples. So this is going to be a trickier example, but might as well start off with the tough problems to show you how to do them. So here we're going to use the first idea of using a fraction, using reciprocals and quotients. Whenever I see problems like this, if I want to substitute in the definitions for cosecant and tangent and get it all in terms of sine and cosine. So the goal of this is to prove why the left is equal to the right. And so we're just going to use some identities and some algebra to manipulate this side and make it the same as the other. So just as a reminder, 1 over sine is equal to cosecant, and cotangent is equal to cosine over sine, and tangent is equal to sine over cosine. So now we can substitute all of this in. We're going to get 1 over sine plus cosine over sine is equal to sine over cosine plus sine. And now we want to combine these fractions to just get two big fractions. So we can get both of these to have a common denominator. So now we're going to switch sine to be sine over cosine times cosine, because these would cancel and we're left with sine. So we haven't done anything to this, we've just multiplied by cosine over cosine, which is 1. And so still equal to that. Now we can combine these on the top and combine this on the bottom. Should probably keep the theta in there too. And feel free to try this out yourself if you haven't already. So if you haven't, pause the video and try to do the rest from where I've already started. So now we have these two big fractions, and now you can do copy dot flip if you've heard of that, or bring it all to just one level. So what I mean by that is, since division, when you're dividing fractions, you can just multiply by the reciprocal. So now it looks like this. So basically we just took the bottom, moved it to the top, and then flipped it, because that's how you divide by fractions. So now we have cosine theta. We can just move this around because we're all multiplying and dividing here. We have cosine over sine theta times 1 plus cosine theta over sine theta plus sine theta cosine theta. So we can simplify this a little bit more. So cosine of theta over sine of theta is equal to cotangent theta. And this right here, this bottom part, is equal to sine times 1 plus cosine theta. And that's conveniently going to cancel out with this thing on the top. So we're going to be left with 1 over sine theta. And then, if we use our reciprocal identity over here, 1 over sine theta is equal to cosecant, now we're left with cotangent theta times 1 over sine theta is equal to cotangent times cosecant theta. So this is what we're left with. That's all simplified. And it just so happens to be that that's what we were trying to prove. And so now we proved that the left is equal to the right because we plugged in some reciprocals, identities, and some quotients. And then we factored and multiplied some stuff and moved it around, and then we got to our goal. So now I'm going to do another problem, which is hopefully going to be a little easier. And so I see some squares. And so try this out yourself, and a hint would be that use Pythagorean identities, because there's a square. So just as a reminder, 1 plus tangent squared theta is equal to secant squared theta. And so that means tangent squared theta is equal to secant squared theta minus 1. And what we're going to do is we're going to substitute this in for tangent squared and try to change this so that we get what's on the left. So cotangent squared x minus tangent squared x is equal to secant squared x minus 1. So that is the same as this because of this identity here. We just substituted in what's true. And now if we were to distribute the negative and rearrange, we can get 1 plus cotangent squared x minus secant squared x. So that's because when we distribute the negative here, we get plus 1, and because of the commutative property, we can move it over here. And so using one of our identities from before, which is the Pythagorean identity, 1 plus cotangent squared x is equal to cosecant squared x minus secant squared x. And now we're done. That's the whole proof. Now, before ending this video, we're going to try one more problem. And to tackle this, we're going to do the same thing as before, which is using quotients and reciprocal identities. And this time, there aren't any squares, so probably not any Pythagorean identities unless it comes up when we're combining fractions. So I'm just going to substitute in some identities. So secant is 1 over cosine, and then equals minus sine theta times sine theta over cosine theta. So that's equal to the top. And now we have 1 over cosine theta minus sine squared theta over cosine theta. And now, combining these, because they have the same denominator, we have 1 minus sine squared theta over cosine theta. And oh, look at that. So now we didn't start off with squares, but when we were combining, we did end up with a square. And we can use a Pythagorean identity to get that this is cosine squared theta. Because if sine squared theta plus cosine squared theta is equal to 1, subtract sine squared theta from both sides, and you get cosine squared theta. So now, cosine squared theta over cosine theta is equal to cosine theta, and that is exactly what we were trying to get. And so, that is how to prove trigonometric identities. So now I hope that you have an easier time proving all these formulas and all these equations, and that it's no longer as confusing.